Hello everybody. So now we are going to discuss one last thing related to the fluid statics, which is the buoyancy and the buoyant force. The phenomena of buoyancy is a very well known phenomena. We all see things that sink in water and things that are suspended in water and things that float on the surface of water. So we know that this is due to the buoyancy or the buoyant force. But what we're going to discuss here is the scientific background of this, why the buoyancy happens and how much force is the buoyant force, and we'll understand some more concepts about this. So first, let's start with a very simple example here. So we have a body that is a solid body that is has density rho s, and it has thickness h, and it's at depth d under the surface of a fluid, let's say water. And based on the concepts of fluid statics that we discussed in this chapter, we can calculate the force on the top surface and on the bottom surface of the solid body. So at the top surface, the pressure is atmospheric pressure if it's open to the atmosphere on the surface. So it's atmospheric pressure plus rho g d. This is the pressure at the top surface. At the bottom surface, it's the same, but it's d plus h because it's rho g d plus h. This density is the fluid density that we include here, and this is something we know from before, that a pressure at a point D, for example, under the surface of a fluid will have a pressure of the atmospheric plus the density of the fluid plus multiplied by GD. So it's the fluid density here, and this is an important thing to keep in mind. And of course, at each surface, this pressure will exert a force. So there is a force due to this pressure on the top surface, and there is a force due to this pressure at the bottom surface. So now the buoyant force is the net force between these two forces. It is the force at the bottom minus the force at the top. And of course, the bottom is larger in value. The pressure at the bottom surface is larger in value than the pressure at the top surface, because here we have H plus D. And here it's only D. So the buoyant force is the difference between the two forces. So it's the bottom force minus the top force. The bottom force is the pressure at the bottom times the area minus the pressure of the top minus area. So each one is multiplied by the area to get the force. And now we can substitute with the values or the formulas for the pressure at the top and the pressure at the bottom, and we can it will end up to be the rho fluid times G times H times A. So this is the buoyant force. The area times height is the volume of the solid particle. So this is the volume of the solid particle. Okay, so we can rewrite this equation as the buoyant force is the rho fluid times G times V. Here is a very important point to notice, that the volume that we have here is the volume of the solid body. The density is the density of the fluid. So they are two different things. This is the fluid density and the solid body volume. So it's an important thing to notice. And if we notice here that the rho of the fluid times the V of the body can be or is equal to the mass of the fluid that has the same volume of the solid body. Okay, again, this rho times V is equal to the mass. We know that mass is density times volume. So rho times V, it is the volume of the liquid that has the same volume of the solid body. Okay, so let's say this, if this body has a volume of 1 liter, then rho fluid times 1 liter is the mass of 1 liter of the fluid. Okay, so this is the mass of the fluid that has the same volume of the solid body. If you multiply it by G, it's going to be the weight of this liquid. Okay, so this is why we are saying here that this is the weight of the liquid whose volume is equal to the volume of the solid body. And this is the buoyant force. So the buoyant force is the force acting on the body that is equal to the weight of the liquid displaced by the plate. Weight of the liquid is the same as the weight of the fluid that has the same volume, so it's the same thing. There is also one more thing to notice here, which is an important thing, that there are two factors that has no effect on the buoyant force. The first is the D. If this is at if this solid body is at high depth or low depth, it doesn't matter regarding the buoyant force. For the buoyant force, it doesn't matter. The second thing, that the buoyant force has nothing to do with the density of the solid body. Okay, so whether it's a dense material, it's high density, low density, it doesn't matter regarding the buoyant force. And from this is what we can put in under the title of Archimedes' principle. Archimedes is the scientist who got the idea of the buoyancy. And the Archimedes principle states that the buoyant force acting on a body of uniform density immersed in a fluid is equal to the weight of the fluid displaced by the body, which we just said in the previous slide, and it acts upward. And this is very, very intuitive. We all understand that it acts upward through the centroid, or the center of mass, of the displaced volume. And this is a very important part of the principle, that it acts on the centroid of the displaced volume. And I want to emphasize on this because we will come to this later, that it acts on the center of mass of the displaced volume. Okay. Okay, so now you might ask a question. So now it seems that the buoyant force has nothing to do with the solid body except with the volume. This is the only thing that matters with the buoyant force. So why do some bodies sink and some bodies float on the surface of fluids or liquids? The reason is that the buoyant force is not the only force that acts on the body. There are two forces actually. There is the buoyant force and the gravitational force, or the weight. So the buoyant force is rho GV, which is the fluid density times G times V. The weight is the same, but it's the density of the solid body. Okay, so we have two forces. They have very, very similar equations. It's the same GV, but this is the density of the fluid, this is the density of the solid body. And so the state of the solid body, whether it's going to sink or to float, depends on which of these two is larger in value. So if and consequently it's the relation between these two densities. If a body has density that is larger than the density of the fluid, then the weight is more dominant, so the body will sink. If it's the opposite, if the fluid has larger density, then it's going to the body will float. And if they're comparable, the body would be suspended, as you see in this figure here. Okay, so this is suspended if the two densities are comparable. If it's the fluid is more dense, the body will float. If the fluid is less dense, the body will sink. Now there is one other thing which is an interesting thing here, that is about the floating bodies. Sometimes you would find the floating body that is part of it, a big part of it is immersed and a small part is floating on the surface, and you might have the other case. For instance, if you see a balloon that's filled with air on the surface of water, it would be barely touching the surface. Most of the balloon is outside, it's not immersed. While if you take a piece of wood, for example, you'll find that a big part of it is immersed and the small part is floating. So the question is why it's different, and the reason is that's something that we can explain using the same equations. For a body that floats, we agree that the density of the fluid is larger than the density of the solid particle, but how much difference here, this is what dictates how or the percentage of the body that will be immersed. So it will be, if the body is under the surface, it will keep rising up and up until it reaches the surface, and then it will stop when it is at a state of equilibrium, which means that the weight is equal to the buoyant force. And the weight is rho of the solid body times G times V. Keep in mind that the weight has nothing to do with the fluid. It 100% depends on the solid body. So whether it's in air, it's in water, if it's sinking, it's floating, it doesn't matter. The weight is weight. As long as it's on the surface of Earth or in Earth, it doesn't matter. So it's going to be rho surface times g times v. While for the buoyant force, we said that it is the rho fluid times g, but it's the volume that's submerged in the fluid. For instance, if you look at this figure here, the buoyant force will only affect this region. This region over the surface is not affected by the buoyant force because it's not under the surface of the fluid or in this liquid. So the volume here, it's only the submerged volume. So we can rearrange the equation to have a ratio between the submerged volume over the total volume. It's equal to the solid density over the fluid density. So if the densities or the solid density is less, but it's not too much less than the fluid density, this ratio is going to be close to 1, maybe 90%, 80%, 85%. So this part here, that's the submerged part, is going to be 85% or 90% of the total volume. So you'll see small part of it is only on the surface. For instance, if you think of a balloon, the example that we just said, if a balloon is filled with air, then the density of the balloon is going to be very, very small. Okay, and so this ratio is very, very small. It can be like 0.1 or 0.05. That's why you'd see all the balloon is on the surface except like 5% of its volume that is submerged. So that's why we can use the densities to calculate the volume or get the ratio of the submerged volume to the total volume. And of course we can find the percentage of the volume that's not submerged under the surface. So one more thing, which is an interesting thinking, which here it's the applications of buoyancy. There are many applications of buoyancy in our life. One of them is the balloon. If you think of a very, very huge body like this, how it floats in air, and the reason is simple. It's the same concept that the balloon, like, if I don't know if it's can be seen here, but in the balloon you'd see here there is a heater, and this heater, the function of this heater is to heat the air so that the density of air inside the balloon is high. And we know that, if you remember, density equals Pm over RT. So the increasing in density, the temperature, the density will decrease. So the air density will decrease, and this is a huge balloon, so the volume of air is very, very big. And so the density of air will be less, and from the buoyancy, or based on the buoyancy, the balloon will float due to the difference in densities. There is one other thing which is an interesting device that's used to measure the density of liquids, which is called a hydrometer. If you're not familiar with the hydrometer, it is like a device that has a shape like what you see here. It has a big part at the bottom, and it has a weight, and there is this long narrow tube that is graduated with a graduation, and it has numbers on it, and it's calibrated, so you know that this for instance, this hydrometer can measure densities between let's say 800 and 1000 kilogram per meter cube, for example. So what we do is you just let it sink, and based on the densities, the hydrometer will and the buoyant force and the mass, of course, the hydrometer will keep going up and down until it reaches a state of equilibrium. And based on the surface or the scale at the surface is the density. So if it's reading something like this, it's 824 kilograms per meter cube, for instance. So the main idea of the hydrometer, or the main concept of the hydrometer, is based on the buoyant force and the gravitational force and the difference between them. And here and if it goes down, it means that more volume is immersed, so it means that more gravitational force. And I mean more buoyant force, and it means that more density, so it's going to read more numbers. If it's not sinking, then it means that it has less density, so it's immersing smaller volume in the fluid. We have one nice example here, which is I think one thing that we always say in our daily life, that you're seeing just the tip of the iceberg, and we use this the sentence because the tip of the iceberg is a small part of the whole iceberg. It's very, very big, but we are only seeing the small part. So this is a good way of explaining why the tip of the iceberg is a small part of it. So let's say we have an ice block floating on the seawater. The density of the ice or the specific gravity of ice and seawater is 0.92 and 1.025. And we have the ice block has it's only 25 centimeters floating on the surface, and the rest is below. We don't know how much height is below, and we want to calculate it. So it's very simple. We will just say that we know the density, so we say that at this state the ice block is at equilibrium. So the weight is equal to the buoyant force. The weight is the weight of the iceberg. So it is it says it's a cubic iceberg, so it's 25 plus h power 3. This is the volume. Or you can just say it's area times height, and the area is the same. So it is the raw ice times g times h plus 0.25 multiplied by area. Okay, so this is the density of the ice times g times the whole volume, rho gv. The volume is area times h plus 0.25. For the buoyant force, it is the rho of the seawater times g times the immersed volume only, which is a times h. We can cancel a and g, so we will end up with the raw water times h equals raw ice times h plus 0.25 raw ice. We know the densities of air, of ice and of water, and we can rearrange the equation to calculate the height, which will be 2.19 meters. And this is a very, very good thing to know, that an iceberg or an ice block that is has only 25 centimeters floating on the surface, it has 5 times this height, almost 5 times, sinking under the water surface. So this is why we say the sentence of the tip of the iceberg. So we will stop here, and next time we will discuss one very short application of the buoyant force on ships and on the bodies floating on the surface. So we'll see you next time. Goodbye.